Hello everyone. Today I'll be presenting my project on predicting cirrhosis using clinical data from a Mayo Clinic trial on primary biliary cirrhosis. Cirrhosis is a late stage of liver scarring causing by a condition like hepatitis and chronic alcoholism and pose significant health risk. Early detection is essential for timely intervention and optimal patient care. Our dataset, which include both trial participants and follow-up cases, provide a robust basis for building a predictive classifier. In this presentation, I will briefly cover data processing, modeling, model building, and evaluation, and discuss how this finding can impact real-world clinical decision-making. Now, I would like to walk you through the exploratory data analysis step I perform on the liver disease classification dataset. EDA is a crucial initial step. It helps us to understand the structure and quality and potential issue in the data before we diving into model building. In the beginning, I import all the package I need in the data analysis, like building model package, like classifier, and also the preprocess to help us encode the target data and mapping out the graph. And now I show you what the data look like. I print out the shape of the dataset using this code and showing that the code has 418 rows and 20 columns. Knowing the dimensions give us immediate sense of how many observations we have and the number of features available for analysis. Following this, I ran this code to check my data type. The output provide me with detailed information on each column, including number of non-null entries and the data type. For instance, while most columns have complete data, I noted that there is some columns like drugs and ascites, ascites and hippomegaly and spiders, where there's fewer missing value. And this indicates that the percents have missing value, which is critical for us to address later on. And also shows us the mix of the data types in the dataset. There's integer, there's float, and object, which means that we need to handle numerical and categorical variables appropriately. And after reviewing the data set structure, I decided to remove columns that we do not contribute any predictive in the later on model. In this case, the ID columns is simply an identifier and does not offer any insight into liver disease. So I delete from here so that we won't affect any later on analysis. And this step ensures us to analysis and modeling focus on features that are likely to informative for prediction. Next, I categorize the features into quantitative and categorical groups. This is vital because for applying a correct pre-process technique later on, the code is like this. Here, I clearly separate the numerical features, which include clinical measurements like albumin from category features such as drug and sex. Define the target variables like stage, set, and stage for our classification task. Knowing which features are quantitative versus categorical helps us later on step scaling, encoding, and even in selecting appropriate model. Understanding the distribution of categorical data is also important. For example, our target variables, the status features, I use this code. The output shows unique values of the stage D, C, and CL. This value represent the different category presented within status, which could correspond to different patient condition and or classification. And recognizing the distinct categories early on allow us to plan how to encode these variables, perhaps through label encode or one-hot encoding, so it can be more effective in the model. And before we moving forward to modeling, it's important to access overall data quality. I did this by counting how many number of missing value in each columns. And also I check the number of duplicate records. And it's pretty good, there's no duplicate. And after completing our exploratory data analysis, I move on to data processing, pre-processing stage. And pre-processing is crucial because it's prepared the raw data for effective modeling by handling missing value, transforming skew, and mitigates the effect of outlier. And for our numerical features, I need to ensure that there's no gaps in the data that might disrupt for our analysis. So I accomplish this by replacing all the missing value with 0 using this code. And for categorical variables like drug, ascites and spiders and hepatomegaly. I replace any missing entries with a string 0. It's different from the numerical dataset. This ensures consistency in our categorical data and prepare these columns for encode later on. Using a simple imputation like this is often sufficient, and when the percentage of missing data is relatively low and will not carry any very important meaning. Next, I needed to simplify our target variables stage. Originally, the stage columns had multiple levels, but for our classification test, we want to a binary target, 0 indicating no cirrhosis and 1 indicating cirrhosis. We define the target variables by assigning a value of 1 only when stage equal to 4 and 0 for all other stages. And the binary encoding is vital because it aligns with our goal to distinguish between patient with or without cirrhosis. And ensure numerical consistency, it's important to guarantee all features we plan to use in our model are in a correct numerical form. So in the quant features, convert all the columns into numerical data types using this code. And addressing the skewness in the data, skewed data can negatively impact model performance, especially in the algorithm that assume that there's a normal distribution. And compute the skewness for each numerical feature using SysPy in the following code. And for the influence of the outlier, outlier can distort the model training and lead to overfitting. So it is important to address this. I use Turkey method to detect outlier, and Turkey rule involves calculating the interquantile range and setting upper and lower limits. Instead of removing this outlier, which might lead to loss of a valuable data, I opt for winsorization. What mean is that it caps extreme values at a specific percentile to reduce their impact without discarding data, removing it entirely. I create a winsorized copy of the numerical data using a 5% limit on both ends. I define a simple function to replace the original value with their winsorized counterpart to ensure that any resulting missing value will again fill with 0. And after preprocessing our data and handling missing value and outlier, I move on to encoding our categorical variables. Since most machine learning algorithm requires numerical inputs, I use dummy encoding to transform category features into binary variables. In my code, I apply pandas get dummy function with a following command. And before diving into model building, I evaluating the balance of our target variables by calculating the mean. The mean is approximately in 0.3445, meaning that there is 34.45% of the sample fall into a positive class, which means 1. And recognizing the imbalance is important that it can influence model performance and might later require techniques such as resample and adjust class weight. Once our dataset is encoded and balanced, the numerical descriptive dataset understanding the relation of our feature. So I draw a heat map of the correlation. And you can see that there is no significant high correlation. So it is pretty good. We start building models. After preprocessing our data, we finally start prepared modeling and evaluation of our model and showing the showing the potential impact in our real world application and explain how to define predictors and target and split the data and build two complementing evaluation pipelines. One using a traditional holdout sample approach with a custom pipeline, and the other is leveraging using PyCaret for automatically model and comparison and tuning. And I start by extracting the predictor X and the target Y from the cleaned datasets. This setup showed us to focus only on the relevant features with predictors ready, and I split the dataset into train and testing sets to create a holdout sample. This holdout sample, which is 20% of the data, and will serve as an unbiased evaluation set. As before, we see that the dataset is slightly imbalanced. So to standardize and balancing the dataset, I use smoked method because different features may have different scale. I standardize the training and testing set using the sklearn standard scaler. And this setup ensures that each feature contributes equally and in the learning process. And the smoke method is named as synthetic minority oversampling technique on the training data. Since our target is in balance, smoke help us to generate an example of the minority class. And the balance seeing the step is critical to prevent our model from becoming biased toward the majority class. And building the pipeline for the holdup sample to I built a end-to-end pipeline and incorporate scaling, smoke, and decision tree classifier. Using a pipeline ensure that each process step is applied consistently during the model evaluation. Here are the code. And after fitting the pipeline on the training set, I will predict outcome on the holdout test set. I then evaluate the model performance by calculating the accuracy and display as a confusion matrix. And you can see that the test accuracy came out approximately 64.29%, and the confusion matrix was here. And now I use PyCaret to evaluating several classification models for predicting cirrhosis key setting, including simple implication like Z-score normalization and small for balancing with a stratified K4 of 5, and get to the result. Our PyCaret output shows advanced model like the extra trees classifier achieve an average cross-validation accuracy of about 75.8% and an AUC around 0.58. For example, while the extra trees classifier reached this number, model like random forest and light GBM performed similar. And in contrast, the dummy classifier only achieved 65.6% accuracy, highlight that add value of our predictive model. Translating these results to a clinical context, consider the following point. Early detection and intervention. Cirrhosis is a progressive condition where early detection can have a significant impact on patient outcome. Even with moderate accuracy around 75%, our classifier could serve as an initial screening tool in the clinical decision support system by flagging high-risk patients, and they can provide prioritized further diagnosis testing, potential leading to early treatment intervention. And in many healthcare environment, resources such as specialist time and diagnosis testing are limited. To automate classifier that reliable identify patient at higher risk can help allocate this resource more efficiently. For instance, patient flag by modeling could receive prioritized for further tests. And the confusion matrix and performance matrix are critical to understand the trade-off between false negative and false positive. In the context, liver disease, a false negative, or a patient with cirrhosis is not identified, could have very severe consequence. Therefore, while an overall accuracy is important, further work may be needed to adjust decision threshold to optimize sensitivity. And in summary, the detail in PyCaret's output provide a comprehensive view of how our model perform under a rigorous testing condition. The matrix ranging from overall accuracy, AUC, to more nuanced measure like recall, F1, and MCC offer insight into both potential and limitation of our current approach. These results serve as a stepping stone toward developing a clinical useful tool that not only aids in the early detection of the cirrhosis, but also support resource optimization and improve patient management in healthcare setting. And that's all.